Hello, everybody. Today, I'm excited to have the opportunity to share my ongoing research entitled Video-Based Deep Learning Model for Automated Assessment of Ejection Fraction in Pediatric Patients. My name is Charitha Reddy, and I'm from Lucile Packard Children's Hospital at Stanford. I have no disclosures to report. Though I'm surely preaching to the choir for this audience, I wanted to briefly review why we wanted to apply machine learning to left ventricular function. As you all know, left ventricular function is used for the diagnosis, screening, and treatment management of all of our pediatric patients. Some challenges associated with obtaining accurate left ventricular ejection fraction are associated with human fractures. The national recommendation is to measure 3 separate cardiac cycles in order to average the ejection fraction, but this is rarely done in clinical practice. The manual segmentation of left ventricular volumes resulting in ejection fraction are time-consuming and are often considered a major source of variability. Previous efforts looking at machine learning and left ventricular function have primarily focused on adult data. In addition, the strategies focus on 2D images in systole and diastole. Pediatric echoes vary significantly for adults from adult echo images for various reasons. There's increased frame rates, increased heart rates, there's a wide range of body surface area, there's a wide range of image quality, and this can impact how machine learning tackles this data. EchoNet Dynamic is a deep learning model published by Ouyang et al. In 2020 that utilized an adult data set of over 10,000 echocardiogram videos in the apical 4-chamber view in order to automatically assess ejection fraction. So we thought, why could we not apply this for pediatric patients? So our aim is to use a video-based deep learning model to automate the assessment of ejection fraction, specifically in our pediatric population. To initiate this project, we focused on collecting echocardiogram data on patients from the age range of 0 to 18 years old with structurally normal hearts only and no prior cardiac surgery. We also collected echocardiograms from multiple different ultrasound machines so that the final model would be vendor agnostic. The breakdown is listed in the table here. We collected a total of 4,400 echocardiograms from 1,923 patients, resulting in approximately 17,600 labeled images. The range of ejection fraction is also listed below. We took the 5-6 area length as our ground truth and have a range of 10 to 81% in our data set. Approximately almost 1,000 patients have an ejection fraction of less than 60%. In the bottom left of the screen, you can see that the breakdown of the echocardiograms used for training, validation, and testing. We used approximately 80% of the echocardiograms for training, 10% for validation, and an additional 10% for testing. In the histograms below, you can also see that there's a slight preponderance for normal echocardiograms or normal values for the ejection fraction, as is expected in clinical practice. We used convolutional neural networks, or CNNs, which is a type of deep learning model, in order to create our machine learning algorithm. CNNs are used to take an input, extract important characteristics, and assign weights or a level of importance to each of them, and then use those features or characteristics to come up with an output that classifies the original image. This very simple graphic illustrates the process. On the left, you can see the image that's input, the hidden layers, which extract features, for example, edge detection, certain variation in colors or grayscale, and then the connected layers take each of those features, prioritize them, and organize them into a model such that you're able to provide the final result, in this case, an output that suggests whether the image is in systole or diastole. We use these types of CNNs in 3 different formats to inform our final model. The first, we tackled segmentation, or the equivalent of a human tracing the endocardial border. We created a weak supervision approach for segmentation by providing the model with two labeled frames, the ones that are typically done by a tech or a sonographer, in which the tracing during systole and diastole is collected, and allowed the model to then extrapolate that for the rest of the cardiac cycle. Second, a model uses spatiotemporal training in order to predict the ejection fraction. The spatial aspect is looking at a single image plane, whereas the temporal aspect looks at neighboring frames. The last is a beat-to-beat identification. Because of the ability to overlay each frame in the video, the model can identify various cardiac cycles to make multiple ejection fraction assessments in the same clip and average them very rapidly, faster than is able to be done manually. In order to apply these CNNs, we had to train against the human standard, and we chose to use the ground truth, or this human standard, as EF derived by 5-6 area length volumes. We trained the model under 3 conditions. 1, to use just an apical 4-chamber clip to predict ejection fraction. Another, as shown in this graphic below, is to provide just a parasternal short axis clip and provide an ejection fraction. And the last condition is when you provide both an apical 4-chamber clip and a parasternal short axis clip and provide an ejection fraction. This video shows the model, which we've now deemed EchoNet Peds, performing the segmentation throughout the video clip. You can see that in both the apical 4-chamber and the parasternal long axis, the blue mask, as we call it, is tracking along the endocardial borders throughout the cardiac cycle and across multiple beats. Now for the big question: how did the model perform compared to its human counterparts? We start with looking at segmentation. Typically, a dice similarity coefficient is used to assess spatial overlap, with 0 having no overlap and 1 having complete overlap with the image. As you can see, EchoNet Peds performed very well in both the apical 4-chamber views and the parasternal short axis view, with dice similarity coefficients at 0.9 and 0.887. Turning to the ejection fraction prediction, which is the most exciting part, we looked at comparisons for a few different things. In the top row, we pulled the data from the original EchoNet dynamic, or the adult model published by Ouyang et al. In 2020. And this shows that the mean absolute error, which is a corresponding value to inter-observer variability, was about 4.1%. The R-squared, which shows the correlation to the human annotation, was good at 0.8. We then used the same adult model and did an out-of-the-box comparison with no fine-tuning and exposed the model to pediatric echocardiogram data. Here, we found that the apical 4-chamber had increased mean absolute error, or increased inter-observer variability percentage, to 6.14%, and had a significant drop in the R-squared to 0.47. The parasternal short axis performed worse, presumably because the adult model had never seen parasternal short axis views, but had a mean absolute error of 9.6% with a negative 0.28 R-squared. If the model was exposed to both the apical 4-chamber view and the parasternal short axis view, the error was still high at 7.24%, with an R-squared that was low at 0.33. In comparison, EchoNet Peds, which was trained, validated, and tested on pediatric echo videos, shows a mean absolute error of about 4% with an R-squared of 0.73, a parasternal short axis, and in the parasternal short axis view of 3.7% with a R-squared of 0.74, and together the mean absolute error is 3.42% with a really nice R-squared of 0.78. I always like to include some levity, and this seems incredibly pertinent with this study. So what are the key takeaways from this? EchoNet Peds nears human accuracy with a normal range of variability. There's low interobserver variability when looking at the model compared to adults. 4% falls well within the range that is typically quoted for pediatric and adult data, where it can go anywhere from 3% to 14%. In addition, one of the major benefits of EchoNet Peds is that you can input only an apical 4-chamber video or only a parasternal short axis video and still estimate an ejection fraction reasonably well by 5/6 area length. This value that you get nears human accuracy. Another major takeaway that we wanted to point out with this study is looking at the difference when a model is trained on adult data versus pediatric data. This data so far elegantly illustrates the importance of using pediatric data sets given the significant differences between the adult and pediatric models. As we think about future directions, our major goals moving forward are to validate this model to make it even more broadly generalizable. In addition, one of the challenges we've seen over and over again with new algorithms that are developed on pediatric imaging is that there's a lack of ability to deploy and make it clinically ready. So one of our focuses is to think about novel technologies like edge servers or federated models, which are better at protecting patient privacy, to test out these types of models and make them more widely available. Thank you so much for your time. And thank you especially to my collaborators, Brian, David, James, and Leo, without whom this project would not have been possible. I look forward to your questions.